Right, script 4a, stop typing, look here, you can finish your exercise later on. So far we have built the code to start with our S2 collection and apply some filters, and we have got our results. So let's say I have my filtered. I found this 30 images. We've not yet seen the images, right? You want to look at the images. So I say, okay, let's go and take a look at what these images look like. So I have my point. To add the images to the map, Earth Engine has this function called Map.addLayer. So we have this Map.addLayer. So this is a function which will add a layer of data to the map. Let's look at the documentation of this. So we need to look at the map module, and there's a function here, Map.addLayer. It says adds a given Earth Engine object to the map as a layer. This function takes many parameters. Only one is required. You can see all of these are italics. One is required, just the object. So let's say I want to visualize this filtered object on my map. Okay. We see something, but not what we were expecting, right? You're expecting some nice looking satellite image, you get black box. The reason you get this is Earth Engine says, I don't know what you want to visualize. Our data, the Sentinel-2 data, has so many bands. What bands do you want? Computers can display only 3 channels of information. Our human eyes can also process only 3 channels of information. We have 3 icons, so we can only see red, green, and blue. Right? Computers are also the same way. You have 3 channels, you can only display 3 bands at once. You cannot see all the information. So Earth Engine says, I don't know what you want to display. I'll just display band 1, 2, and 3 by default. So if I see the layer, so I have a new layer here, layer 1. There's a settings button. And you can see it's displayed band 1, 2, and 3 here. So I can say I want to see maybe red, green, and blue. So I want to see a true color thing the way we would perceive the data. So I want band 4, 3, and 2. So I can go and change it. So I want band 4, 3, and 2, and I can click apply. Some change, but still black. Right? When you display the data, Earth Engine is saying, I'm displaying this band 4, 3, and 2. The data type of the band is int16. That means you can store values from 0 all the way to 2 to the power 16. That is 65,000. So that is the range of values this data can store. And it says, I don't know what is the actual range of data. And so it says, I will display the minimum as 0, maximum is 65,000. And the actual data, the pixel values are reflectances. In Sentinel-2 data, you get the reflectances multiplied by 10,000. So the pixel values here, if the reflectance was 0.2, you'll get value like 2,000. The reflectance is 0.5, you'll get 5,000. And most of the Earth's surface has a reflectance between 0 to 3,000. Right? So your pixel values are actually 0 to 3,000 or 0 to 4,000. But Earth Engine doesn't know that. It says I have your data type, which can display 0 to 65,000. I'll display the whole range. And that means there's no data for most part of this, and that's why it's black. If you use any desktop software, you never have to deal with this in desktop software. So let me do the same thing in QGIS. I have QGIS. You can do the same thing with ArcGIS if you want. I have some data. And let's say I want to load this data into QGIS. I do not get black. Right? Why do I get this nice image? Because the desktop software will say, I will actually look at the image pixels, compute the statistics, and display this, and find out the data range of the values. Let me see what QGIS did here. You can see here, it says min is 900, max is 2000 for red band. It computed that. How did it compute? It says, I will compute the statistics, find out what is the value at the bottom 2 percentile, and what's the value at the top 90th percentile. So it's computing the statistics. This is called a 2% stretch, a 90th percentile stretch. So it says, I'll compute the stats, find out the min value, which is the bottom 2 percentile, the max value at the 90th percentile and use it. And why this? Because there are outliers, right? There are most pixels, some are 0, some are very bright. I just want to find out the actual data range. And it did that. In Earth Engine also, we can do this. So if I come here and do the settings here, you can see the default range is 0 to 65,000. But Earth Engine says I can apply a custom stretch here. If you want the same thing that QGIS did, I can do a 98th percentile stretch. You can see it found the value, and now when I apply it, you'll see similar results. You can also do a different stretch. So you can do a 1 standard deviation stretch, find the values, find the mean value. The minimum will be 1 standard deviation less than average plus average. If we do this, it says the range of values are between this range, apply it, you can see now something that looks like our satellite image. You can also adjust the values as a custom stretch. So you know, by experience of working with the satellite data, you know that most of the values will be between 0 to 3,000. So you can just say, I want to display this between 0 to 3,000. And I apply this. And now I can see it looks like a satellite imagery that. And I want to do 432. Right, so now I have something that looks much nicer. Right, so I basically have to set this visualization parameters. This is also one of this kind of learning curve that you have to do in the desktop software. The software kind of handholds you and does this thing automatically. Earth Engine, you have to specify this yourself. Once you get used to it, you'll learn this. It really depends on the data. If you're visualizing temperatures, you'll say my min-max value is 0 to 40 degrees Celsius or something like that. It depends on the data. So you can figure out what is the range of the values. When I'm working with a new data set, I often just go and do a 1 standard deviation or a 98th percentile stretch here, find the values, and then I can tweak that to get the visualization. And remember, this, what we did, is only changing the visualization. It's not changing the pixel values. So when you're analyzing, it's not changing the actual pixel value, just showing you how the data is visualized to see the information. So I've come up with a nice visualization, and again, you send your script to a friend, and they run it. You're back with black boxes, because whatever you did was kind of happened in your browser, right? It's not in the code. So let's encode this in our code itself. The Map.addLayer has a second parameter called visparams, visualization parameters. And it says this is a dictionary that you can specify with all the parameters you want. Okay? So let's see how we can specify this. So I'll define a dictionary. We need to give the parameter. Min, 0. Max, 3,000. Bands, what bands you want. We'll say band 4, 3, and 2. Okay. So now we have visparams. We can now say my second parameter is visparams. It's just a variable name. You can choose whatever you want here, right? We just defined this. Now when we run this, you'll see the actual image, right? So now you'll send your code to somebody, they can do this. We encoded this one. By default, when you add a layer, it is called layer 1, layer 2. You can see there's a third parameter here, which says name. You can actually change the name of the layer. And you can see it says filtered collection. Right? So you're adding the data. At the least, you should do 3 parameters: the name of the layer, the data, the visualization parameters, and the name of the layer. And you can display that. Questions on visparams? This is probably the most confusing part. So if you're not sure, please ask questions.
The order of the bands doesn't matter.
It does matter. You can. This is the red, green, and blue band. So we're displaying R, G, and B band. So this says put the band 4 in the red channel, 3 in the green channel, and this blue channel. So this is called true color composite. You can also do a false color composite where you display, let's say I want to do 843, which is near infrared, red, and green. So you'll see something that highlights vegetation. So all the stuff in red is healthy vegetation. So this is called false color composite. So if you want to do an FCC, traditional remote sensing parlance, you can change the band combination that you want here. Yes?
You assigned minimum 0, maximum 3000. Or what is the base for 3000?
Yeah, so what we want to know is what is the reflectance of pixels in this region. Normally the reflectance of materials in kind of city landscapes are between 0 to 0.3. That's a range of reflectance. So I want my min to be 0, max to be 0.3. But if you look at the data, you see there's something called scale here. And scale is this. That means when you get the image, the values are reflectances, but to get the reflectance, you have to multiply the value by this to get the reflectance. So in your image, your pixel value, when you look at it, it'll be 3000. And say, what does 3000 mean? Well, you multiply it by this, it becomes 0.3. So that's your reflectance. Yeah. Any question, any idea why ESA would do this? Why would they not just give us an image with reflectance? Why they expect us to do the extra work?
For memory issues, because yeah, we have all this processing power, but yeah.
Yeah, so to store a value as integer, you can store in 8 bits, right? 1 byte or 8 byte, 1 byte you can store integer. If you want to store a floating point value like 0.3, you need 64 bits. So 4 times, or at least 4 times more storage. You can see this was 16-bit data, so you store values from 0 to 65,000. If you store integer, you can store integers up to 0 to 65,000 in 16 bits. If you want to store value like 0.3, you need 64 bits. So the same data, if you want to store as floating points, you need 4 times the storage. ESA is collecting 5 petabytes of data every month. So instead of storing 5 petabytes, if they give us floating points, they have to store 20 petabytes. So they say, we will not spend this extra storage, you can do it yourself. Right? So that's the reason a lot of providers will give you the data which is an integer, you can convert it to floating points. And this is again, I worked on the aerial imaging team at Google. It's a big consideration. Our camera systems, they say if you want to have a camera system that takes floating point, we need very big hard drives. So we just store this stuff as integers, you can store the data much in a smaller way. So a lot of times that's the reason to do this. What are we seeing on the map? Our filtered collection is 30 images. What do you think we are seeing on the map here? Yeah? The most recent one? Any other guesses? Mean? Any guesses? We have 30 images. An Earth engine cannot do 30 images. It's a flat 2D canvas. Yes?
That's occurring with an algorithm behind the scenes.
It's some composite that's occurring. To kind of illustrate this point, let me delete this geometry, and I'll draw a polygon that goes across 2 scenes here. Okay? Let's run this. So what you're seeing on the map here, you see some image here, some image here. What Earth Engine is showing is you have a bunch of images that I want to display. I can only display 1 pixel at each location. It's creating something called a mosaic. It says, I will take the topmost pixel from your stack of images and display that. The topmost pixel, by default, the collection is sorted by date. So you have the latest imagery on top. So here, say in this location, I have 30 images. I'll display the topmost pixel. In the neighboring, there's another orbit here. So it says, okay, there's a topmost pixel is here. So I'll just say I have all these things. I'll sort images by their date, and I'll take the topmost pixel. So what you're seeing is the most recent pixel from the stack of images. The traditional remote sensing required you to do this mosaics. What you would do is you will say, I want to work with this data. I will go and look at the catalog. I'll find the most cloud-free scenes in each of these regions. I'll put them together and say, I'll fill this my region of interest with the most cloud-free data. I'll arrange them in different orders and say, this is what I get. But there are many regions where you cannot get cloud-free data because there'll be cloud here, and you have no mosaic, no order of images that make sense. So that was an old way of doing things. Still, many people say, show me how to create a mosaic of images. That was the old way of doing. The new way of doing things is first find images that make sense for your analysis. Let's say you're working on this data. I want data for September 2023. So you find all images that are match your criteria, and then you create something called a composite. A composite is a way to take all the data you have and get a statistical output. So you can say, instead of displaying the topmost image, bottommost image, I'll display the average value here. So the clouds are very bright, the shadows are very dark. The average value will be likely a cloud free. Right? You can do a yearly composite. So you say I have year images worth a year. This is what this region looks like a year on average. If you're studying agriculture, maybe do a monthly composite, or maybe do a seasonal composite. So the new way of thinking, doing remote sensing, is figure out what date range makes sense for your analysis, and then, so once I found the images, I will create a composite image. Doing composite was very, very difficult. If you want to create a composite for this region, we have 30 Sentinel-2 scenes. You'll download 10 gigabytes of images each, and so I have this pixels. I will try to create a composite. It's going to take a day or two to run on a machine. So that's why people never used to do this composites. But with Earth Engine, you have the power to do this. Let's create a composite and see how that works. So we have our data. We'll say I have my filtered collection. Earth Engine gives you a way to create different composites. You can do mean. So it'll take per pixel mean of the whole stack and give you the mean value. In Earth observation data, we typically don't do mean, we do median. Do you know any reason why we do median, not mean? Yeah.
It indicates the outliers.
Yeah, so our Earth observation data is heavily affected by outliers. Cloud shadows, clouds, those are outliers. Let's say we have some data values. Say this pixel that we're capturing has maybe value of 2500. So one observation was 2500, next image has maybe this, the third image is cloudy, right? So you will have 9000. The fourth image, again, normal image, you say this. Fifth image is, very cloudy again. So now you do mean of this, you will get value that is much higher than 2500, right? Because you have outliers. But if you do median, you'll sort this and pick the middle value, which is like 2500. Right? So median is more robust to outliers. So in data that is affected by outliers, like our optical data, you use median. If you're working with SAR data, that is mean is fine. If you're working with climate data, mean is fine. Right? So stuff that doesn't have outliers, you can use mean. Yeah.
Oh, I was just going to add that one more thing is in mean, you can actually get a value that never was actually observed. Because you can get like 1 and 3 and 5, and if you do a median like 3.5 or something like that, it never actually occurred in observation. With the median, you're almost guaranteed a value that was actually observed in the time series.
Almost, I think.
Yeah, almost, yeah.
Yeah. So there is something called medioid, which is also more
Much
robust
better,
to this. But yeah, I think median just removes the outlier, so you're much better. Let's visualize this. So I want to visualize a composite. I'll use the same Viz params. And you get a cloud-free composite. What happened was Earth Engine said there are 30 observations at each pixel. In the course of a year, I'll compute the median value and display this. And it just happened. You can see it happen in real time. Like you can zoom in and you can say, Earth Engine is now computing and give you this cloud-free composite. Right? This was impossible before Earth Engine. Now, since this is possible, this is the new way of doing remote sensing. So you first start your project, see what date range makes sense for your project. If you're doing urban change, maybe year to year makes sense. If you're doing agriculture, do a seasonal composites. Figure out the date range. You can, if you're doing like weather data, weekly composites are fine. So figure out what date range makes sense for you. Filter the data. Don't care what's in the data, just do a composite. And you get kind of the statistical observation in the time range, and then you can work with those data. The advantage of this is now you're working with cloud-free data. There are no pixels that are cloudy, so you can compare year to year. And you can do your analysis. If you have clouds, you have no data, so you cannot compare. Questions on median composites? Let's do the exercise 4C. Now you're going to really see the power of Earth Engine. Let's say you have a task. I want to do change detection. I want to know how my city changed between 2019 and 2020. You can say I will create one median composite for 2019. I'll create another one for 2020, add them to the map, so I can now compare the data of how the city changed between those two dates. So try out this exercise 4C. The first step, delete the geometry, drop a point at your city, wherever you want to do this. The code you run will give you the 2019 composite. Copy paste this code, paste it below, change the data into 2020, run it. You'll see two images. I want both images of 2019 and 2020 on the map. So you'll see how your city has changed between those 2 years. Try out 4C in this. And make sure you are working on this repository G introduction. Some of you might have my end-to-end Earth engine. The material will start diverging now. So make sure you are using the G-introduction repository. We're doing 4C in part 1. There are more efficient ways of doing this, but for this exercise, you can just copy paste and just have 2 blocks of code. One is for 2019, same thing, copy paste, do 2020, and then you can add both to the map.
But how do I know that they're comparative?
Yeah, you can turn this on and off. You can see?
Oh, this way.
Yeah, or you can just even do transparency. So you can zoom in someplace and you can either turn off or you can just do before and after.
I'm just having trouble. So we have to delete the geometry first,
Yeah.
right? Okay, so then
Drop a point first.
right, with this or with
Yeah,
the
this
inspector?
one. No,
Oh,
this
okay.
one.
That's why I was.
Yeah.
Okay, so then now it's
Yeah. Yes.
but now when we do this, it's adding the geometry where it's adding it to
Yeah, yeah. You can see the kind of how you can do this. Here you have 2019. You copy paste the code, change the date range to be 2020, change the variable name, do a composite, change the name here, make sure you add the new data here. And once you have it, you'll see there are 2 layers. You can turn them on and off and see the changes. Maybe zoom into a place where you know something has changed. You can turn them on and off to see the kind of things that have changed within 1 year in the city. You can see the changes.
Or I guess the other trick is you could also use a little slider.
Yeah, you can also use the slider to swipe and see the changes. Yeah, yeah.
I was trying to. I had it right, okay, and then I was trying to. I said, okay, that's good, but there wasn't enough change, so I wanted to go back a year.
Yeah, so you can go up to 2017, I think, because this is 2015. You can go up to 2015 and try this. Yeah.
Okay, so thanks to Sam, I have this, but how do I go between? Oh, this is how I go between them. Gotcha.
And again, Bangalore is a very fast-growing city. There are a lot of changes that happen. When I was working at Google, I was to be responsible for acquiring satellite imagery. And we would see, what's a good time to acquire new imagery for a city? And for Indian cities, even every 3 months is not enough. There are new flyovers and new buildings. And then we look at Amsterdam, and nothing has changed in 2 years, right? So it depends on where you are and how fast the growth is. So again, if you don't see enough changes between those 2 days, maybe change the date range. You have Sentinel-2 from 2015 till yesterday, right? So you can kind of change the date range to any. A few more minutes to do this, and then we'll do the last script before the break. Another funny story, I had an intern who worked with me, and he obviously learned Earth Engine, and he was still a student, and his professor gave a task for doing some change detection as an assignment. And again, people were to do whatever tools they wanted. Everybody was downloading data and doing this, and it was, the servers were taking a long time to download. And he knew Earth Engine, so he just did this assignment, and then his classmates found out that this guy can do this analysis. And he said, I just spent a few hours doing everybody's assignment in the class using Earth Engine, and just 2 minutes versus spending the whole night trying to download and process data. So again, if you've done this on a desktop, you realize how powerful this is, that you are just able to just drop a point and get a change detection going in just a few lines of code. Okay, next script, you can stop, save your work. Let's move to the last script. We have a few more things, but we'll finish it after lunch. Let's do this feature collections. So we'll work with 5A now. Everybody stop typing, save your work, eyes here, and we'll learn about feature collections.